Well, good morning, everybody.
Good morning.
Happy Mondays.
Happy Monday.
No? Let's finish up chapter 11, and then hopefully there'll be a little bit of time today to give you a boost on your chapter 11 homework. All right, let's do this Wednesday, I think, because the exam's on Thursday. Please tell. Okay, so I remember vividly posting the topics to your exam. Did that really happen? Okay, good.
Yeah.
I'm not that old yet. Back when we did conservation of momentum in a straight line, we set up this, kind of idea that whatever we had to begin with is what we needed to end up with. And when it comes to angular momentum, we're going to do exactly the same thing, using, of course, the symbol for angular momentum, which is L. Only, what do you remember about conservation of linear momentum? I mean, what needs to be happening in order for us to apply conservation of momentum? Okay, so there was this whole inelastic thing, wasn't there? But inelastic and elastic referred specifically to what?
The collision.
A collision, right? Some sort of interaction between objects.
Do you mind turning on your mic on and off?
Now it's off. Now it's on. So this collision that was taking place, this interaction, right? I'm imagining one object and another object coming in and striking each other. I mean, I can see that. But angular momentum? What does a circular collision look like?
Planets. Planets colliding.
Planets. When worlds collide. What's an angular, is an angular collision like one spinning bicycle wheel hits another spinning bicycle wheel? No. That's a linear collision, right? Even though the objects have angular momentum, their center of masses are still moving in a straight line towards each other. That would be straight up regular conservation of momentum. So, what does an angular collision look like? Somebody mentioned gears. Okay? So, one of the things that pops into mind when I kind of my go-to example in my brain for an angular collision. Remember in physics, collisions are interactions. They're not necessarily when things touch each other. But if I want something that's rotating, that has angular momentum, that then interacts or collides with something else that's spinning, my go-to example is an automobile's transmission. And I know this looks like a really complicated picture and all that sort of stuff. But deep down inside of your car, you have a transmission. And as you drive your car, you can feel, if you have an automatic transmission, you can feel the car shifting gears, right? You start off kind of fast and the engine revs up a lot and then it kind of switches down so that you can then go faster and switches down as you go faster again. This gearing mechanism is, it's there to provide efficiency so you can get the power of the engine to the road in the right ways. But when you change a gear, when you go from one set of gears to another, or even try to disengage the engine from the transmission and the thing that makes the car go, think about that. When you pull up to a traffic light, right, you hit the brakes, when you come to a full and complete stop, can the engine of your car be connected to the wheels?
No.
Your engine's still going, isn't it? And if it were still connected to the wheels, what would your car be doing? Trying to keep going, right? Okay. So there's a device in the transmission called a clutch. What the clutch does is it engages and disengages the engine, okay, from the rest of the car. And by show of hands, how many of you drive a manual or know how to drive it?
First car?
It's going to be my first car.
Yes,
my
good.
only two.
Okay. Manual cars are awesome. Right? In a manual transmission car, you actually have 3 pedals. So it requires 3-legged people in order to drive?
Yep.
No, right? You just need to learn your heel to toe, right? Skills. But, yeah, I learned how to drive my manual transmission in San Francisco.
Oh.
You must be an expert.
Yeah. I love my dad, but man, he was mean. So, that third pedal is what operates the clutch. You push that pedal in at any speed, and the engine disengages from the universe, okay? And so, this clutch, this assembly down here, has got some friction pads and some springs and other things. I don't want to get into it too far. But basically, what it does is it allows a smooth connection to your engine that's constantly turning around at various RPM, depending on how much throttle you've given it, right? And then it allows a smooth connection between the spinning flywheel of the engine and the rest of the car. And anybody that's ever learned how to drive a manual transmission knows what happens when you slip the clutch, right? And you pops out and you kind of don't hit it quite right. All of a sudden the car will lurch, right? And depending on how well the transmission of the car is tuned, then that lurch will either be very violent and you'll finally get going, or the car will just simply stall. The engine will just go, you know what, I give up, right? And it'll just turn off. So this is an angular collision. We have a disc connected to the rest of the car that's not spinning. We have a part of the car's engine that's rotating around, the drive shaft. And we've got to get these two pieces to come into contact with each other and begin moving as one. So that's about the closest example I can give you to a direct angular collision. All other angular collisions are a bit more abstract than that. Somebody mentioned planets. Conservation of angular momentum is used a lot in spaceflight for stabilization and changing the direction of motion for a planet in a slingshot maneuver. So that's one of them. Other examples I have involve the Olympics, Winter Olympics, ice skate. I'm looking forward to the Summer Olympics coming up in 2020. Climbing for the first time will be in the Olympics, so that's just going to be glued to the screen. But in the Winter Olympics, you have the figure skating. And in figure skating, there is a particular move that they're required to do. I believe it's during their both long and short programs. My wife knows more about this than I do. I watch it to appease her after that, and otherwise I'm pretty bored. But basically, if you've ever seen a skater, they do this move where they're skating along. I'm going to have to simulate it here. They're skating along in a straight line across the ice, and they're doing something kind of like that. Right? Okay, their hands out. And how does this move end? You're gliding along, all graceful, and then what? Yeah, they'll pull, they'll kind of almost come to a stop, but really they'll kind of turn. They'll begin a rotation, and as they begin that rotation, they'll pull their arms and legs in, and what happens to the speed of their rotation? Right? Looks like an auger right straight through the ice. Okay? So, what I've done is I have brought my Michel Kwan simulator. Okay. It consists of a stool that can rotate around, okay, and these masses right here. I do have physics muscles, but are these significant? Yeah, it's pretty good. Yeah, this is, what, about 10 pounds? 8? So, what I'm going to do is I'm going to sit on this stool and I'm going to hold these out, okay, to the side. I'm going to give myself a little bit of speed, and then I'm going to pull them in. All right, and what happens to my rotational speed as I pull these in? Yeah, I sped up. I better go the other way before I get sick. All right, throw them out, slow down, pull them back in, speed up. That right there was an angular collision? Can I use that word? I mean, nothing flew out, right? Nothing. What was the thing that changed?
Yeah.
Well, actually, the center of mass didn't change. That's interesting observation, right? I took the masses from here to here, but the center of the system stayed in the same place, right? So what is it? Moment of inertia change, didn't it? So remember, one way to write conservation, or to write angular momentum, is to write it as a moment of inertia times an angular speed. So we've got both initial and final. I better put initial and final on my moments of inertia. So in this situation, like an ice skater or me on the stool or something like that, the thing that changes pre and post, initial and final, is the moment of inertia. This is really what you want to be looking for in most conservation of angular momentum problems. You're not so much looking for things coming into contact, although it does happen, but more you're looking for changes in moment of inertia. What shifted in the situation before and after that gave rise to that change? So let's do the example of me sitting on this stool, right? We can solve our statement right there for the final angular speed. We're going to compare initial angular speed to final angular speed. So if I do that, I divide both sides by the final moment of inertia. I'll end up with final angular speed over there. And let's, excuse me, let's just kind of, we need to talk about what this initial and final moment of inertia is. When I began, right, I had my arms outstretched, right? So the moment of inertia of this system consists of several parts. We'll break it down, okay? So there's the part of Mr. Balo on the stool, right? Okay? So how do we find the moment of inertia of Mr. Balo on a stool? We go to the table? Yeah. Does the table have any listings for Mr. Balo on the stool? No?
I don't think it's supposed to.
It's not, the table's not posted? They put it on Dropbox. Did it not show up on Dropbox?
It's showing up on Dropbox.
Yeah, it should be in for the day of that lecture. It should be right in that PDF. But it's in your book anyway. A slightly different one. I showed you both, but the one I showed you, one I posted on Dropbox, the one that's going to end up on your exam. So there's nothing listed, and if you wanted to be really offensive, we get into a discussion of whether or not I am a solid cylinder or a sphere. We'll not talk about that. But instead, what I did is I went ahead and just kind of measured what it was. So let's just pretend that the moment of inertia of Mr. Balo sitting on a stool is 3 kilogram. So that's kind of my central, me and the stool and everything together. But if we're going to find out what the initial total moment of inertia is, what else do we have to include? We've got these masses, right, don't we? Okay. Now, what about my arms?
Slender
What can we mod? Slender rods?
Slender rods.
Did you hear that? No, actually, we'll just model them as massless rods. We'll not worry about that. We could do the slender rods, right? But I'd have to know how long they were and what their mass was. I don't know what that is. Let's just pretend I got physics arms, no mass, no muscles, no nothing, right? Okay, we'll just worry about these. Okay. So what is the moment of inertia of one of these masses that's sitting at a distance r from the center of rotation? Is there anything on the table that says a heavy mass at a distance r? No. So what do we do when we have a single mass? We're going to treat it like a point. And what's the moment of inertia of a single mass?
MR squared.
It's just mr squared. It turns out to be exactly the same as like the thin hoop or something, right? So that can be a little bit confusing, but mathematically they're identical. So initially, how many of those point masses do I have? We got 2. So I'm going to have 2 mr initial squared plus the 3, right? So the 3 is the Mr. Balo, and the 2 are the masses, right? And then afterwards, right, the change that's taken place, what's the one thing that's changed? Yeah, the distance, right? We've taken it from out here to in here. Okay, so that radius is really the only thing that's changed. If we assume that the initial radius was 1 meter, okay, so from center line out to where I'm holding it is about 1 meter, and we assume the final one, if I just kind of bend my elbows in, was, I think I said 30 centimeters, so 0.3 meters, then we can chuck all of those values in. What did I use for the masses? I didn't write that down. What I did find out, though, is that this number for my arms outstretched was 9. And this number, so we should be able to figure out what that meant. This number turns out to be 3.54. And when I come back over here, I have a 9 over a 3.54 times whatever my initial angular speed is. Okay, so what is this trying to tell us right here? That 9 over 3.54, is that a number bigger or smaller than 1? It's bigger than 1. So we've got a ratio that's bigger than 1 times our initial speed is our final speed. What's that trying to tell us? Yeah, I sped up, right? When I go from a larger moment of inertia to a smaller moment of inertia, the angular speed is going up. Conservation of angular momentum is about this trade-off between moment of inertia and angular speed. If I reduce my moment of inertia, my angular speed has to go up. If I do it the other way, if I increase my moment of inertia, my angular speed has to go down. The total amount of angular momentum before and after is conserved. It's exactly the same. We trade between different aspects of it. All right. I think we'll get to it a little bit later, but on your homework there is an example, I think, of this transmission where you've got 2 disks that are on the same axis and they're all coming together. All right. Got something else I want to show you here, okay? And it's the reason I've been trying to warm up my shoulders all morning long. Don't get old. That's my advice. 35 was a really bad year, okay? After 35, my body parts started not working anymore, and my shoulders started going bad, so I've got to be careful now, not warming up. I've got my bicycle wheel, okay, and you see this one's got masses in it on the outside, okay? Those are there to make sure that the moment of inertia of this particular bicycle wheel is really large. You want the moment of inertia to be as big as possible, because what I want to show you is another aspect of conservation of angular momentum. The direction, the vector nature of angular momentum must also be conserved. Got my rotating stool, right? It's fairly frictionless, okay? And what I want you to do is get your right hands ready, okay? Because I'm going to be asking you to apply your right hand rule for angular momentum, and it's angular speed, angular momentum is the same thing. So, same direction. So you're going to be wrapping your fingers around, right? I want you to show me before and after what the direction of the angular momentum is. All right, so here it goes. This thing spun up. Okay. If I hold it like this, what direction is the angular momentum? It's pointed down, isn't it? Okay. Now what I'm going to do is take my feet off the floor and I'm going to turn this over. Now what direction is the angular momentum? Not of the wheel, but of me. It was also down. Right? So, I turned the wheel over, and did the wheel's angular momentum direction change? Yeah, right? It went from down, and as soon as I turned the wheel over, it's pointed up now. However, angular momentum must be conserved. So, the wheel imparted angular momentum to me and caused me to spin which way? The right way. The original direction. The total angular momentum between the wheel and myself is the original angular momentum the wheel had. Did you hear me grunt?
Yes.
It was hard to turn that wheel over. It really fights that change. I'll demonstrate in just a bit. But let's see this again, right? Let me spin this back up. Right, now which way is the wheel's angular momentum pointing? It's spinning, I don't know if you can tell, spinning that way. So now it's pointed up, right? So what direction should I be spinning when I turn this over?
You should be on.
Ugh! And am I?
Yes.
Turn back over and I stop.
Yeah.
Turn back over.
Yeah.
And I spin. Turn back over and I stop. Okay? And that,
No.
I grant you, I'm a wimp. Okay? Right? But on Saturday, I climbed 540 vertical feet with two 10-year-old girls and another 52-year-old guy. And my daughter and a friend of mine and his daughter. And man, that was a hard climb. All the people up rocks. I'm kind of tired. All right. So you grab that. Are your wrists okay? Okay, grab it with both hands. Okay? Now try to move it and point it somewhere else. How would you describe that experience? Not easy. Right? Okay? The wheel has an angular momentum, right? Let's see, let's point the angular momentum at you. So the angular momentum is pointed at you right now, right? Okay? Be careful. I'm going to take it from that direction. I'm going to try and point it over there. And I want you to see what happens to me. Are you ready? I'm going to try and move it really fast. Okay, I didn't exaggerate. Okay. And if I do it again, okay?
Yeah, I noticed.
This thing really fights. It wants to keep that direction of angular momentum consistent. Let's spin it back up again. All right. Now, I'm going to hold this out as level as I can, and I'm going to let go. I want you to watch what happens.
Geez. Oh, shoot. Oh, God.
What is it not doing? It's not falling, right? It is turning around. It is going that way, right? But if that wheel weren't spinning, and I tried to do that, what would happen? Yeah, see, it just falls, doesn't it? Okay? So let me show you. There's no hijinks going on here. Well, just physics hijinks. So what I've got here, right, is a way to hold this on a string, right? So if I, it just falls if I do that, right? Important safety note, don't let this get caught in here. And don't get your fingers caught in here either. Too close. There we go. Right? Okay? It's not falling over. What it's doing is it's twisting around. This is called gyroscopic precession. Okay? And what it is the result of the wheel trying to keep its angular momentum the same. But it loses to gravity and to torque. Let me see if I can't help you through this idea. What I want to do is I want to show a video that has this going on with a much bigger, much more massive, much more dangerous situation. I'm going to show you a video from Veritasium. Does anybody know Veritasium? Dr. Derek Mueller. He's a fantastic educator, smart guy. Why he's not wearing a helmet in this video is beyond me. Like, smart guy, didn't get it. Okay, so let me switch this.
So is there the reason why there's like a push and a pull because of the air being sucked up through the wheel?
Nope. We'll get there. You know what? It would help if we had some sort of log. I was testing with captions.
I am here at the University of Sydney where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a meter-long shaft. Can you imagine trying to hold this out horizontally with just one hand at this end? It is virtually, it is impossible, okay? Now I'm going to let go. You going to be able to hold this at all? I'll try. Can you lift it out? Make it horizontal. Hold it, hold it, hold it. Come on, just try. I want you to hold it out horizontally. See if you can. Hold it, hold it. Oh, come on. What I'm going to do is I'm going to spin this up to a few thousand RPM. And then I'm going to attempt just that, to hold it from one end and have it out horizontally. Five, four, three, two, one, boom. I'm going to let go with my left hand. What you'll see is that the shaft remains horizontal. You can see it going around there.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme.
I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck.
But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning.
Let's prove that I can lift it just this end without it spinning. Here we go. I mean, it's just kind of awkward with the hand.
It's really heavy too. Careful.
Woo, just barely. Oh goodness, do you even lift? I do not.
Undaunted by my lack of strength, I'm going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the best chance of success.
Give it 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go! That was perfect. And I'm going to release my left hand, and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1. Beautiful. Let's go again. In 3, 2, 1. Nice. 3, 2, 1. It feels incredibly light as I do that.
All right. So, what the heck is going on? Physics. It's always physics, isn't it? All right. So let's pull up the blank. So, what do we got? We have this. What I'm going to do is this is the bicycle wheel seen edge on. So basically, we're looking at the bicycle wheel edge on, right? And here's the handles I have attached to it, okay? And the support, the place where I'm holding on to it, is on one end, right? I had that thing in my hand, and I was just sort of holding it right there, right? So, I mean, technically there's a force and a normal force and everything. That's not really important. What's important is the fact that gravity is acting on the center of mass of the bicycle wheel. And that gravitational force, the weight of the bicycle wheel, is acting at a distance away from the support. So if I have a force and I have a distance and there's a perpendicularness to them, what am I going to have?
Angular momentum.
Torque. That's a torque right there, right? Independent of the wheel spinning, there's a torque that is applied right there. And that torque is our cross F. Here, we'll use the full vector cross product. So in this case, R cross MG. MG's pointing down. All right. Oh, by the way, if we we'll do that in a minute. All right. So if all I've got is no spin, right, and I just support it on one side. Let's see if I can get sure. This side right here. Okay, I just support it on the left-hand side. Then this thing is just going to fall straight down, right? So what is the magic about the wheel spinning? When it comes to the spinning wheel, the wheel is going to have an angular momentum. So let's say that the wheel in our picture here is spinning so that the top side is coming towards us and the bottom side is going away from us. So if we use the right-hand rule to figure out the direction of the angular momentum, what would that be? Top side coming towards us, bottom side going into the... So the angular momentum is pointing to the right. Okay. I don't know if you remember, but I dropped this on you back when we started talking about angular momentum the first time. The torque, right, from Newton's second law, Newton's second law in rotational terms, right, is, again, like Newton's second law in linear terms. It's a mass times a change in motion, the acceleration, equals the sum of forces. In angular terms, that mass is moment of inertia. The acceleration is angular acceleration. And instead of forces, we talk about torques. But I also told you that torque causes changes in angular momentum. This is, again, analogous to the linear case, where when Newton first wrote it down, he was really thinking about it in terms of momentum instead of mass and acceleration. So whenever there is a torque applied, those torque, if they're not balanced, right? If there's an unbalanced torque, if there is a sum of torque that's not zero, it's going to change the angular momentum of an object. So in the case of the spinning wheel, all right, now that we've given it an angular momentum, okay, and there is a torque that is applied, it's going to instead change the angular momentum. And instead of having the wheel fall, it's going to cause the wheel to precess, to go around. Why doesn't it fall? Why does it precess? What direction is the torque acting on our wheel in this picture? Okay, yes. It's got to be perpendicular to what? The distance and the force, right? The cross product. And which right-hand rule do we use for cross products? Hitchhiker or handshake? Handshake. So if we go R, shake in the direction of R, rotate our hand around in the direction of the weight, the mg, what direction is our finger pointing? In to the screen. The direction of the torque is into the screen. And the direction of the torque is exactly the same as the direction of the change in angular momentum. So for a spinning bicycle wheel, okay, so this one's spinning such that our angular momentum is pointed, I want to get the diagram just like that, okay? So now, if I hold this on one end, right, it precesses in the direction of the torque. I grab the other side, it'll go the other way because I changed the direction of the radius. Can I pass it under my leg? No. So, anytime, so I've seen these setups in places like museums, natural history museums, science museums, that sort of stuff. I remember I was in Seattle visiting my wife's family, and we went to the Natural History Museum downtown Seattle, and they had one of these in there. They had a little like belt that you could hold the wheel down on, and it would spin the wheel up for you. Only it was kind of slow. You know, it was designed to keep kids safe and all that sort of stuff. And so I got in line to use the apparatus. There was a bunch of school kids going through that day, so there was a bunch of like 3rd and 4th graders all lined up. So I got in line. Right? And when I got up there, and I grabbed the wheel, and I saw the belt was going so slow, so and what the kids would do is they would come up, they'd put the thing on spin it up, right, okay, and then they would they wouldn't really know what to do with it, right, because they weren't reading anything, and the teacher wasn't telling them anything, right? So basically they'd go spin it up, and then they pull it into their chest to use, break it, right, on their, so they have these burn marks down their jackets and stuff. It's pretty fun. So I get up there, I grab the wheel, I go, that's too slow, and I step aside, and I just flip this wheel over, right? And they had a chain and a stool and everything right there to do all the experiments with. And so I started doing those experiments, right? Like, you get this stool out, you get a lot of fun. Right? You grab it like this, take your feet off the floor, you can actually twist this thing around, and it will cause you to rotate and stop. There's one direction that's preferred in all this, but right? Just applying some torque to that thing. It's changing my angular momentum in response to this thing, right? Okay. I took this and I spun it up really fast, right? Their bicycle wheel was a little bit smaller than this one. And I started doing these tricks, right? Okay. I was younger then, so I'd pass it underneath my leg and all kinds of. And the kids were going wild, right? Oh, right? They just thought that was the most amazing thing. So I was there, they kept me at it for like 5 minutes, right? They're like, oh, do it again, right? And so I was getting pretty tired. I was like, okay, I'm done, right? And I gave it to the next kid, and they're like, they tried it and broke their fingers. I can't remember what they did. And then the teacher and the parents came over, okay, it's time to go, right? And one of the moms stopped by. They have such nice people that work at this museum. I don't work here. I'm on vacation. So, and then some more kids ran up, do it again. So I did it again, right? And they're like, okay, we got to catch up with our class. And I thought, okay, here's my escape. Around the bend comes another class of 30. Oh, look at that. And they come running over and they made me do it. I was there for like 40 minutes, right? So be careful about what you know. All right. This concept of gyroscopic precession, conservation of angular momentum, it crops up in a lot of different places. So I've actually got a couple more YouTube videos, and I've got some more examples I want to show you about conserving angular momentum, about the direction that angular momentum points, and why that direction is so important. I don't particularly have a preferred order to do this in, so
Wait, what was that?
do you want to learn about bicycles or helicopters first?
Helicopters.
Helicopters? All right. So on Smarter Every Day, which is another YouTube channel I highly recommend, okay, you can, there's a whole like 7, Destin's got a lot of videos on this channel, but you can, there's a 7-part series in helicopter physics, and he does some really deep dives into the physics behind helicopters. I've taken the part where he's talking about gyroscopes and precession and helicopter stability. So we're just going to kind of look at this little section. You'll be missing sort of some parts before. They're not terribly important. What I want you to focus on is when he pulls out the bicycle wheel with his friend. Okay, they're going to talk a little bit about how helicopter blades work and how there's a 90-degree offset between input and what actually happens. And then they'll try and explain it using a bicycle wheel.
A helicopter, and I simply want to make a maneuver, and I want to tilt the helicopter up and forward.
Walk with, it's a pretty curious kind of gait that they have, and by gait I mean the way that they walk. So they'll be sitting here with their thing, but if you watch their center of mass, it's totally straight. Okay, they're moving, and if they sometimes when they'll try to turn. Okay, they'll be doing this and they want to go over that way, and if they don't throttle down, they keep it at high throttle, you watch them turn, and it's like they'll overcorrect. It's almost like they're being tugged, okay, by the back thing. Well, what's going on there? at full throttle, you've got this angular momentum vector pointing out of your back. And as soon, just like that wheel, when I tried to turn it quickly, and it fought me, right? And it was throwing me around, it's exactly what happens to them. So they either walk in a very straight line, okay, because they're kind of forced to, right? They got the angular momentum vector pointing out their back. Or they have to throttle down so they can turn their direction and then throttle back up. So they're constantly, whenever they want to turn a direction to blow the leaves around, they have to throttle up and down. So for the regular homeowner, you buy usually a small handheld one, okay, to blow the leaves off. And in truth, I bought mine for fluid dynamics experiments, but that's a different story. But you used to buy them, and the fans were mounted vertically like this, okay? You're holding it, and you had your little trigger, and you're trying to swing it back and forth. But with the fan mounted vertically, okay, what are you constantly fighting against? What direction is the angular momentum vector of this wheel pointing? Pointed off to the right now, but if I turn, right, now it's pointed this way. Was that a change in angular momentum? Yeah, and so what needs to be applied in order to change that angular momentum? Torque. So you're constantly having to input torque, which means you're constantly having to input force, which means your arm's getting tired, right? As you're out there trying to, I mean, the device is supposed to make it easier to rake the leaves up, right? Not harder. And so manufacturers figured this out. People are complaining of fatigue in their wrists. So they took the fans and mounted them like this. Now, with the fan mounted horizontally, you swing it back and forth. Are you changing an angular momentum vector?
No.
Okay? As a matter of fact, you stabilize the angle at which you're holding the output, which is what you need to do anyway, right? And now I can sweep it back and forth without ever changing the angular momentum vector. So I get more stability, less fatigue, when the blower's fan is mounted horizontally in the device as opposed to vertically in the device. So my leaf blower broke doing fluid dynamics experiments. So I had to go get a new one. And I went... I like to think I'm a nice guy, but I do have a mean streak in me. When I go to stores and the poor person walks up and says, "Sir, can I help you?" Yeah, if you ever see me in a store, run. Okay? Because this poor young guy came up and he was like, "Sir, can I help you?" Because I was in this section and I was looking at all the blowers. He came up and he says, "Can I help you?" And I said, "Yeah, it depends. Can you tell me where all the leaf blowers are that conserve their angular momentum vectors?" This is true. I do things like this. And the poor guy was like, right? I think it was one step from security, right? And there was like a pause of like, it was just the awkward 5-second like, right? He didn't even get a chance to get the word "what" out. When through the aisle, you know how like in Home Depot, Lowe's, all those different places, they got those aisles and you kind of see through them? And sometimes they got so much stuff on it you can't see through, but you can hear the marital disputes happening on the other side. So through the aisle, I couldn't see what was going on, but through the aisle, I heard someone shout. And they said, "He wants one with the fan mounted horizontally." I was like, "What? What? Right? And around the bend came one of my Physics 4A students. And he had the lecture like 2 weeks before that, right? I was like, "Oh man, you can win!" Right? Okay. And this poor other guy was like, "What are you guys on about?" Right? We're high-fiving, talking about angular momentum. So, yeah. Life is fun. All right. So the other place that gyroscopic precession seems to be involved is with bicycles and bicycle stability. Now, a lot of people think incorrectly that the spinning bicycle wheel lends itself to stability. And I'll admit that it's a part of what keeps a bicycle stable, but it's not what stabilizes a bicycle. So So I want to play a video for you from Henry Reich, who is the guy that does the Minute Physics channel on YouTube. And he's going to explain bicycle stability to you. What I want you to look for is the interplay between many of the things that we have talked about in this class. So we've talked about center of mass, we've talked about where the supports are located with respect to the center of mass, and we've also talked about, today, gyroscopic precession. So look for those three things.
This is kind of related back to when you had the wheel. What happens if you were to have both two at the same time? Would there still be a balance? Or
Two wheels spinning. Are they attached to each other somehow, like along their axis?
Are they in the same direction?
Attached.
Okay, so if they're attached on the same axis and they're spinning opposite directions, then the total angular momentum is 0. Because the directions will be opposite and they're spinning the same speed. But if they're both pointed in, the angular momentum is pointed in the same direction, it will double the angular momentum and make it even harder. Third stuff. So the answer is it depends. Angular momentum messes with your brain.
Bicycles are one of the most efficient and
sorry YouTube people, you should have been to class. I've had to pause during all those videos because the YouTube copyright bots come after me. So I'm allowed to use it because it's a course, class, public domain, all that sort of stuff, but the bots go to all, they take down the videos and it takes a week to get them back up. The first three here, this is a problem of kinematics. Okay? And I did examples back in when we were doing chapter 10 together. I always feel like it's a natural place to do the rolling motion along with angular kinematics, which is why I lumped them together there. But this really is hearkening back to chapter 10. This problem, okay. You are allowed to hate me for this problem. It's all right. Okay? Because what does it just look like from the picture?
Energy.
Projectile motion? Right?
Yeah,
Energy?
projectile motion.
Something, right? So
It's mixed up.
this thing is rolling off of that roof, right?
Yeah.
So as long as L is there, right? As long as it's rolling along the roof, I would use conservation of energy, but consider the angular energy as well. We did stuff rolling down inclines, right? So I would do energy up there. Now, they want to know how far horizontally away from this roof this thing lands. So how do you think you're going to have to go about doing that?
I'm gonna just cover a ball of paint roll off the floor and then where it lands, I measure it.
Just measure it, yeah. But how do we predict it?
And energy.
Can conservation of energy help us here? For the part where it flies into the air, we want to find out how far horizontally it goes. Conservation of energy can get us the speed that it hits the ground with, but that's not going to help us. Yeah. This requires kinematics. We need to know time. We need to know how long it takes for this object to fall down from the lower level of the roof, the lowest point of the roof. Once you've got that time, right, it's in free fall as soon as it leaves. Don't forget to bust it up into vector directions, vertical and horizontal, like we did in chapter 4. Why did I give this problem to you?
Yeah.
I wouldn't purposefully stick a projectile motion problem on the test. However, I need you to remember the stuff we've done before. Because next unit, we're applying a lot of these different things, right? So I stuck this one in here to keep you in memory of projectile motion. George?
So the rationale behind using kinematics is because nothing in conservation of energy has resistance.
Yeah, it does if we're talking about work done by friction or something like that.
Yeah, that's what I was saying.
And we've got, so you could like try to say, well, I got this point, and I know that this is going to be MGH, right? So I can find out how fast it's going when it strikes the ground.
Yeah.
But they don't care, like, there's nothing in work energy that would tell me how far horizontally it went.
Yeah.
To really do that, I need to use this. But that means I have to find my time.
Yeah.
And how am I going to find my time?
Okay.
Right?
Alright.
But I need to get V naught X and I need to get V naught Y. Right? Because this thing's going to leave the roof going at some angle. So, yeah. I don't apologize, but I do warn you. Okay.
Oh.
You can't hate me for this one. This is pure awesomeness in a problem. Okay? Like, if you understand this problem, you should have no trouble on the exam. Like, seriously, this problem has got like almost everything except kinematics in it. Okay? It's mostly energy, but it has you thinking about forces in circular motion because we're doing a loop-de-loop down here. I think the first part of the problem is asking about, how high does it need to be in order for it to just barely, it says, on the verge of leaving the track. When this thing's right at the top of the track, we've done the free body diagram of this before. What direction is the gravity pointing? It's pointing down, isn't it? What direction is the normal force pointing? Down. What direction is the acceleration pointing? It's going in a circle, right? So there's got to be a centripetal acceleration acting downwards, right? So if it's on the verge of leaving the track, just right at the moment it's going to fall off, what can you assume about the normal force? It's 0. Okay? So set up the standard chapter 6 Newton's law problem there. Set n equals 0, and don't forget that your centripetal acceleration is equal to that. So you'll know what speed it has to have at that point. That becomes your final speed. Where are you going to put the initial position? Up at h, where it starts, and you're going to solve for h. Don't forget to include the fact that it's rolling down, right? So you're going to have a 1/2 I omega squared term for your energy. So what changes in part B? For part...
It's rolling, it's frictionless?
No, it's not frictionless. In order for it to roll, there needs to be friction, but you don't have to include the work done by friction. When friction causes something to roll,
Is there 2 R's?
when friction causes something to roll, it's taken care of. The only friction you need to include when doing work is kinetic friction. The part that's different in part B is they're asking now about this horizontal position at Q. They want to know what the normal force is right there. Is that right? Yeah. Horizontal force component acting on the ball at Q. That's a normal force. So if I draw the ball at that side, I've got a normal force acting like that. What direction is the acceleration? Towards the center. What's Newton's second law have to say about that? It's the only one pointing in the horizontal right there. Is there gravity? Yes, but is that in the horizontal? No. Okay, so I'm not going to worry about it. This gravity right there, it's causing tangential acceleration. But what's causing the centripetal acceleration? What force points towards the center? I mean, I know it's the centripetal points, but which one is it? It's the normal force, right? Don't go inventing another force for the centripetal force. Find a force that's already there that points towards the center. In this case, it's the normal force. And again, don't forget V squared over R, right? And you'll find V for the they'll give you a height 4 times the radius, right? And then find the V that it's going to have at Q. And then you can find out what that normal force is.
But it's normal force 0 and part A.
because it says it's on the verge of coming off. An object will stay on the track if there's normal force at all points. The point where it disengages and falls off the track is when the normal force disappears. Right? The definition of normal force is that the two surfaces have to be in contact. And if they're no longer in contact, they're no longer pushing and pulling. So they've set the condition for part A.
What does it mean by the circular loop has radius big R, and then a ball has radius R, and then it has 2 greater than sign?
Oh,
Yeah.
yeah. What they're trying to say is don't worry about how big the ball is.
Okay.
Right? This R, that sign in physics means R is a whole lot smaller than big R. Right? Normally we'd say R is less than R, right? That one means it's really, really small, and so you don't have to like subtract out the radius. You don't have to find the center of mass of the ball, right? And then subtract out that distance to find out actually how high the center of mass is. Don't worry about that. Just assume that the ball is at twice the radius above the ground when it's at the top of the loop. Their picture is misleading, right? They show that ball being kind of large compared to the loop. What they're trying to indicate is, don't worry about it. Treat it like a point particle. And away you go.
Wait, what does that say? This loop? Oh, can you go back to that for a second? No, that was MG.
MG.
Oh, MG, okay.
Yeah. When something's not important, I tend to write it very messy. Okay. And then we finally start getting into kind of what I consider the real meat of chapter 11. What is this problem? It's a cross product problem, right? Straightforward, mathy one. Here, okay, how do we find the rotational inertia of this entire thing? We've got the origin, the axis right there. So it's all point masses at a distance d. So what's the moment of inertia of a single mass? Just mr squared. So to find the total moment of inertia of this thing, oh look, I'm showing you all the answers. md squared for the first one. What's the second one going to be? m2d squared. So this one is md squared, but this next one right here is m2d squared. What are you going to remember to do? Square the 2 and the d, right? And then what would the third one be? Right? And then you would add all of those together to find the total moment of inertia. And then magnitude of the angular momentum, I omega, magnitude of the angular momentum. So you're just finding the angular momentum sort of straight calculation at that point. I forgot. I could switch to student view at this point, but I'm not going to. So yes, there'll be numbers up there. You can see them on YouTube, blah, blah, blah. But make sure you understand what's going on.
It's fine, because there's different numbers.
It's some of the, if the problem, but some, not all are randomized. All right, ice skaters, holding onto a pole, do not try this at home. What's changing? The radius, and so therefore the moment of inertia of the system, right? Okay, so as treat them as point masses as well, right? But as they change the distance they are apart from each other, it's changing the moment of inertia of the system. It's going to speed them up, slow them down. Here's the problem that is the transmission problem. 2 disks that are connected. I'm going to attempt to draw this. I apologize for what you were about to see.
Are you really sorry, Mr. Bill?
No. So there's one disk. See, I'm going to screw up. Nope. Can't get their centers again. Oh, there it goes. Okay. So, do you get the idea? they're different sizes, aren't they? Okay. Well, they've got different moments of inertia, right? Okay. In part A, they're both spinning in the same direction. They say clockwise, counterclockwise. Okay. I've tried to draw this in 3 dimensions, right? Okay. So they're both spinning. They have different angular speeds. And so when we set up the conservation of angular momentum equation, before they come into contact with each other, what's the total angular momentum? They're both spinning. They're separate from each other. They both have moment of inertia and they both have angular speed, right? So the total angular momentum of the system would be the combination of the individual angular momenta that they have. However, after the collision, treat them as one object. They're stuck together. So how would I write that down? If it was 2 masses colliding and staying together, what would you do afterwards? Just add the masses together, right? So this is 2 spinning things coming and sticking together. What are you going to add together? Mass in rotational terms is moment of inertia, right? Treat them as one object with a combined moment of inertia. Did the moments of inertia change in this problem? No. We're not changing the size of the disks. We're not changing their mass. Moment of inertia is independent of how fast it's rotating. So we're not changing the moment of inertia this time. What we're doing is we're keeping them separate and then combining them. And then I'm going to have an omega final here. I've left the vector signs on these because in part B, what's different? The direction of the second one or something like that, right? Okay. One of these is different. And so what do you think you're going to have to do with that number? Treat it, make it negative. You call one of them positive and the other one spinning the opposite direction, you better put in a negative value. So I had you do bullet pendulums in chapter 9 with linear momentum. This is that problem, but this time you have a pendulum that has a moment of inertia and you're solving it in an angular form. Does the bullet have angular momentum as it strikes the block? Yes, it does. Why? The bullet's going along this line right here, isn't it? And as it strikes the block right at this point, right there, does it have V? Yes. Is that V at a distance away from an axis of rotation? Yes. And how do we write the moment of inertia of like a point particle moving at speed V? Not moment of inertia, angular momentum. Do you remember? Remember MVR? The bullet has momentum mv. Distance r away. One definition of angular momentum is take the regular momentum and multiply by its distance from the axis. So there's the angular momentum of the bullet. What's the angular momentum of the block before they collide? 0. Why is it 0? It's not moving. Okay. After the collision, the bullet, the block, everything is stuck together. So, what will the moment of inertia be after the collision? It's going to be the moment of inertia of the bullet plus the moment of inertia of the block plus the moment of inertia of the rod. That is not a massless connector there, is it? So go look up. What are you going to do for the bullet and the block? What equation would you use for those? mr squared. You just treat them like point particles. They're masses at a distance r away from the axis. But what about the rod? What are you going to have to do for that one? You're going to have to go to the table and look up a slender rod pivoting about one of its ends. 1/3 ml squared, I think, if I remember correctly.
So when when we're looking at collisions, when we have something that is a point of like a fixed point of rotation, we're looking at conservation of our angular momentum. But when there's no axis of rotation, two things are colliding, we're looking at just conservation.
Yep. Yep. So basically 2 objects coming straight into each other and bouncing off. That's linear momentum. Okay, so that was some help with your homework. What are you going to bring to me on Wednesday? Questions. Either questions on homework. Remember to ask questions about all the things, not just chapter 11. See you Wednesday.